Next, we're going to talk about physical and chemical changes as well as physical and chemical properties. These are two very related ideas as in how we test them and identify them. A physical change is one in which the matter actually stays the same. I know that kind of is a lame definition, but what this really means is we actually have the original matter in the same bonded state. A great example of this is if you evaporate water. It goes from being liquid water to water vapor. Another example that's even a little bit more visible is if you actually take an ice cube and melt it, turns into liquid water. You can also refreeze it back into its original state. That's something you can test at home. It'll still be water the whole time. So that's just a physical change. The original matter can be, in other words, I would say recovered. Meaning we can just kind of, without doing any chemistry, we can turn it back into what it was. So you could take some tap water, freeze it, and then allow it to melt again, and it'll still be water the whole time. No new chemical formula can be written. So in the example that I've been talking about, if we take liquid water and we freeze it, that's all we're doing. We didn't write an actual different chemical formula. We started with liquid water, so I have a little L indicated here, and we changed it to a solid, but it's still H2O in both cases. Chemical changes are changes where the matter is no longer the same. In other words, we've detached atoms and reattached them in another way. The original matter, in order to actually get it back, you would have to do something pretty extensive. You'd have to do like another set of chemical changes usually. So there are actually reversible chemical reactions, but for the most part, our original matter is not simply recovered by doing something simple like when we talked about freezing and thawing out water. Bonds between the atoms have been broken and reformed, and a new chemical formula can be written. An example of a chemical change that we will talk about a little bit this year is something called the Haber process. They actually use nitrogen gas, which is N2. They react with hydrogen gas, which is H2, and they make ammonia out of it, which is NH3. And this reaction is really important in the making of fertilizers. Just balance that guy out. We'll talk about that later too. But in order to, when you actually do this reaction, you're breaking bonds between the initial N's and the initial H's, and you're forming whole new bonds in the NH3s. So we actually have totally different bonds, and new chemical formulas are able to be written. So to do a quick little rundown of some examples here, physical versus chemical changes. If we melt some butter on warm toast, that melting is simply physical. When we light a match, we actually are doing a chemical reaction. Cooking of pancakes, when those little nice bubbles form, you're doing a chemical reaction there. This is a little confusing because a lot of things we cook you boil water for, and boiling water is a chemical, or I'm sorry, is a physical change, so you're not actually doing a chemical reaction there. Cooking of pancakes, you really actually do create new matter. Delicious matter. Tarnished silver. If you've ever seen silver in your house, it's turned that brownish color. It's kind of like analogous to the process of rusting. That's an actual chemical reaction that's occurred. Freezing a popsicle, that's just a phase change. That's physical. Milk going bad. That is a chemical change. You do not want to drink that milk. It is not the same. Physical and chemical properties are things that kind of can usually be tested by physical and chemical changes. A physical property can be observed without doing any chemistry, so without actually doing a reaction. So if you melt something, or if you simply look at its color, or if you're seeing if salt dissolves in water, those are all things that you're doing that aren't actually causing chemical changes. So when we just mix things together, that's not a chemical change. Just look at color, that's not a chemical change. We measure the temperature at which something melts, that's not a chemical change. For our chemical changes, we actually are talking about how substances react with one another. So you might hear things like, oh, iron will react with oxygen and form rust. That's actually a chemical change. When iron reacts with oxygen, you have solid iron reacting with oxygen in the air, and it makes something called iron oxide. So iron oxide is actually a different combination of iron and oxygen. They're bonded together in a different way. Saying something is inert or not reactive, or saying something is corrosive or highly reactive. Those are all things that you can say that are talking about how a material reacts and therefore referring to chemical changes. So to classify some of these, if we wanted to measure the mass of some copper wire, measuring mass is simply just a physical property. If we wanted to measure boiling point, all we're doing is boiling something. That's just a physical change. So it's a physical property. Baking soda reacts with vinegar to make carbon dioxide gas. So that fake volcano reaction is a chemical change. The solubility of sodium chloride in water is 40 grams per 100 milliliters of water. This is just talking about dissolving salt in water. It can be separated back out by physical means. So that's a physical change. Density is also something that we're simply measuring volume, and we're measuring grams or mass. So that's a physical property as well. What you'll notice when we talk about chemical properties, you're typically looking for the keyword reacts or thinking about how something bonds. Physical properties can be classified as extensive or intensive. These words aren't actually used a lot on a lot of the tests. You'll take the concept of an extensive or intensive property often is. An extensive property actually depends on how much of the material you have. So if you have a large piece of something and you measure like mass or weight, that's going to change if you break it into smaller pieces. The amount of heat you can get out of a piece of wood. A large piece of wood would give you more heat or more energy than a smaller piece of wood. So the amounts of the stuff that you have are dependent the properties that you have are dependent on the amount when you're talking about an extensive property. An intensive property are properties that do not depend on the amount of matter that you have. And these can actually be used to identify matter because no matter how big your sample is, they're always the same. Great example of this is density. You guys have heard that the density of liquid water is 1 gram per centimeter cubed or 1 gram per milliliter. So no matter how much water you have, that's always true. The boiling point of water is always 100 degrees Celsius. Doesn't matter if you have a ton of it or just a small amount of it. This is also going to be true typically for color. So these don't depend on if you take a large piece of a rock, any individual piece of that rock has the same density and would have the same boiling point. It doesn't matter if you break it down into smaller pieces. So in the previous slide, if we go back for a minute, we can look at some of our physical properties. The mass of a piece of copper wire is 255 grams. Now, if we go back, remember, extensive properties depend on how much of the matter we have. So this is an extensive property. Boiling point, doesn't matter how much of the stuff you have, that's going to be the same in a small sample or a large sample. Solubility is actually the same. It doesn't matter how much you have. It's that ability of how much you can put in there. The density of something, also going to be intensive. If you wanted to look at something like just volume or just mass, those are extensive, but their relationship through density is going to be intensive.